Okay, so Chapter 18, Section 2 is about carbohydrates. Carbohydrates are defined here as organic compounds including sugars and starches. The energy held in their chemical bonds is used to power cellular processes. Trying to figure out here when I want to say something about the word carbohydrate. I think I'll go ahead and do it right now. The word carbohydrate means carbon and water. Everybody's familiar with the term. You need to stay hydrated. You need to rehydrate. Do not want to dehydrate. That always refers to water. Hydration. Carbo refers to carbon. And if you are familiar with, and I think you would know from Biology 103, for example, glucose. Let's look down here just a little ways. Here's glucose, and this is a model of the molecular structure of glucose. And if you'll look at it, you'll see that it has 6 carbons, and you will see that it has 12 hydrogens, and it has 1, 2, 3, 4, 5, 6 oxygens. So you might recall from Biology 103 that glucose is C6H12O6. If you take the 6, 12, and 6 for carbon, hydrogen, and oxygen, those are all divisible by 6. So if you take C6H12O6, which is glucose, and reduce that down as low as it will go, something we call an empirical formula, it reduces down to CH2O. Okay, C6H12O6, 6, 12, and 6, all divided by 6 to give you 1, 2, and 1. So that means it's carbon and H2O. It's carbon and water. That's what carbohydrates are. And that is how they got the name, carbohydrate. So carbohydrates are ingested in a variety of forms. Complex carbohydrates include polysaccharides. Now, saccharine means sugar, poly means many. So a polysaccharide has many sugars that are chained together, and each link in the chain is something called a simple sugar or single sugar or monosaccharide. Okay, so starch, for example, like when you think about potatoes and pasta and rice and bread, those are starchy foods. Starch is one form of carbohydrate. It is a polysaccharide. And starch is simply a bunch of glucose molecules connected together in a chain. Again, I've posted some extra videos for you that came from Chemistry 105 that will show that in more detail. Okay, so starch from plant foods. Glycogen is another chain of glucose, and glycogen should sound familiar to you. When we talked about hormones, we talked about how insulin and glucagon cause our body to either store excess glucose in the form of glycogen or break glycogen down to release sugar into the bloodstream. And specifically, it's glucose. So when you eat meat, it will have some glycogen in it because one of the places that animals store their excess glucose is in the form of glycogen in their muscles. And that's what meat is. It's muscle. So whether you're eating starchy plant foods like potatoes or rice, or you're eating meat that will have some glycogen in it, not a lot normally, but some, then you're getting polysaccharides. Most foods containing starch and glycogen have many other nutrients, including valuable vitamins and minerals. The simpler carbohydrates include the disaccharides, that means double sugars. This is going to be the lactose found in milk, so it's milk sugar. There's cane sugar, which is sucrose, and then there's beet sugar and molasses. There's also malt sugar, which comes from the breakdown of starch in grains like barley. Then there are the monosaccharides, the single sugars or the simple sugars. You find these in honey and fruits. But also a disaccharide can be split into two monosaccharides. So, for example, cane sugar. When you just talk about going and buying a bag of sugar, you're buying sucrose, and sucrose is a combination of glucose and fructose. Now, fructose is commonly known as fruit sugar. Honey has a good bit of fructose in it. Fruits have a good bit of fructose. And of course, there is the high fructose corn syrup that's used to sweeten a lot of things. A lot of people try to stay away from that. Digestion ultimately breaks the carbohydrates all the way down to monosaccharides, which are small enough to be absorbed into the bloodstream. So whether you eat starch or whether you're getting glycogen in meat, or if you're eating double sugars like sucrose or lactose in a dairy product, ultimately those get broken down all the way to the simple sugars. There's a little talk here about sugar substitutes to provide concentrated sweetness so that you need fewer calories. Stevia comes from leaves of an herb. They say it's 30 times as sweet as table sugar. Aspartame or NutraSweet is actually a dipeptide. It's two amino acids. They are, I know this if I can pull it out of my head right now, phenylalanine and aspartic acid. They say that it's 200 times as sweet as sugar. Saccharin is 300 times as sweet. That's the pink packs. What is that called? I don't use any of these. Sweet and low. Sweet and low is saccharin. Sucralose, 600 times as sweet. Sucralose is sold as, oh my goodness, I can't find the name. I'm sure y'all know. Interesting note, sucralose for a long time was only made in one place in the world, and that was in the little town of McIntosh, Alabama. It's in Washington County. It's just north of Mobile. I think there's another plant making it now somewhere in Asia. Sucralose is derived from sucrose, but it is chlorinated, and so the body does not treat it the same as it would sucrose in terms of calories and in terms of raising blood sugar. Now, all of these things that it says are as sweet, or 30 times, 60 times, 100 times as sweet as sugar, honestly, that's subjective. There are none of these things that I can tolerate. None of them taste sweet to me. All of them are bitter. That includes stevia. It includes NutraSweet. I can't stand them. The only thing that I've found is monk fruit. And I'm not sure if it's more accurate to say that monk fruit contains something called erythritol, which is a sugar alcohol. And I think I explain a little bit about sugar alcohols in those other videos, those extras. If I didn't, I need to go back and talk about that. Anyway, now I'm reading reports that erythritol is causing people to have blood clots, so I may have to rethink my use of monk fruit. But if you're like me and all these other artificial sweeteners, or, well, stevia is not artificial, but it's gross. If you don't like the taste of them, give the monk fruit a try, see if it works for you. Cellulose, another complex carbohydrate or polysaccharide that's abundant in food, but it's not digestible by humans. It is plant fiber. It gives celery its crunch. Lettuce makes it crisp. We humans cannot digest cellulose. Most of it passes through the alimentary canal largely unchanged, but it provides bulk. We call it fiber or roughage, and that gives peristalsis something to push what we eat all the way through the alimentary canal. Then there are some other um, plant carbohydrates that give us fiber. There's hemicellulose, there's pectin, which is common in jellies, lignin, which I associate that more with wood than other plant fibers. But all of these are polysaccharides, but we do not have the enzymes to digest them. Now, some of that bacterial flora found in the colon can break some of these things down, at least to some extent. It often leads to production of gases and acids, so that's why high fiber diets can lead to excess gas production, cramping, bloating. All right, so how do we use carbohydrates? The monosaccharides that are absorbed from the digestive tract include fructose, galactose, and glucose. Liver enzymes will catalyze reactions that will convert fructose and galactose into glucose. So let's take a look at this. Here we see molecular structures of fructose, glucose, and galactose. If you take a look at them for a minute, you'll see that all three of those have the same molecular formula. All three of those have 6 carbons, 12 hydrogens, 6 oxygens. The difference is in where those carbons, oxygens, and hydrogens are relative to each other. Fructose stands out the most because what you'll see here in glucose, if you look right up here, you see carbon double bonded to oxygen at the top. In galactose, the carbon is also double bonded to oxygen on the top carbon. But you'll notice that in fructose, the carbon that's double bonded to oxygen is not up here at the top. It's the second carbon down. Now, in organic chemistry, we refer to a carbon that's double bonded to an oxygen and then has a hydrogen on that carbon. That is called an aldehyde. So glucose and galactose both have aldehyde groups in them. For that reason, they can be referred to as aldoses. But the carbon with the double bond oxygen in fructose does not have a hydrogen on it. It has 2 other carbons bonded to it. That means that this is a ketone. And you've probably heard of ketones. So fructose is not an aldose, it's not an aldehyde sugar, it's a ketose, a ketone sugar. So, easier to see the difference in fructose versus glucose. In galactose, the difference is much more subtle, and it has to do with the location of this hydroxyl group. On carbon number 1, 2, 3, 4, the fourth one down from the top, excuse me, the OH, the hydroxyl, is on the left-hand side of the molecule, whereas in glucose, it's on the right-hand side. And so that is the only difference in those. Now, there is a word worth knowing for these 3 things. Fructose, glucose, and galactose all have the same molecular formula, C6H12O6. But where those atoms are bonded to each other, in other words, how they are arranged in 3-dimensional space, is the only difference. And the word for things that have the same molecular formula but a different arrangement is isomers. I-S-O-M-E-R-S, isomers. So glucose, galactose, and fructose are isomers of each other. They're made with the same parts, just put together in a different order. And the enzymes that were mentioned up here, enzymes in the liver catalyze reactions that convert fructose and galactose into glucose. Those enzymes would be classified as isomerases. Something that ends with ACE is an enzyme, and it will convert one of these isomers into another isomer. And there is more on that in those extra videos. Some excess glucose gets polymerized, in other words, chained together to form glycogen in a process called glycogenesis. I told you about this way back in the first chapter of the semester. It is subsequently stored in the liver and muscles. The reverse process is glycogenolysis, which means the splitting of glycogen, and it can be broken down to make glucose that is then released into the bloodstream when we need it. Body can only store a certain amount of glycogen, and excess glucose reacts to form fat, and that process is called lipogenesis, and the fats get stored in adipose tissue. All right, so we have carbohydrates, we have starch. They don't mention glycogen, but it would fall into the same category. We have these three disaccharides or double sugars, sucrose, maltose, and lactose. Digestion breaks these things down. Starch and glycogen are broken down to glucose only. Sucrose, again, a disaccharide, consists of glucose and fructose. Maltose just has glucose in it. Lactose has glucose and galactose. But then remember that the galactose and the fructose can be converted into glucose. So those are all monosaccharides: glucose, fructose, galactose, and ultimately they all become glucose. So what's done with that? Well, we can use it for cellular respiration. In other words, we can, as the common term is, we can burn that sugar. Not a literal flame, but we break it down and produce carbon dioxide and water and release energy from it. Of course, we exhale the carbon dioxide in the water. There's some water vapor when you exhale. We can also get rid of the water in the form of urine. But where do the carbon dioxide and the water go when they leave our body, when we exhale them? Well, plants absorb them and turn them into new glucose and starch, starting with a process called photosynthesis. And then we eat the fruit of the plant or the plant leaves themselves, and they are back into us as starch and sugars, and we break them down and put them back out as CO2 and H2O, which the plants absorb and give us more food. Or maybe a cow comes along and eats one of those plants as grass and uses it to build muscle, which we eat as hamburger meat or a steak, or a chicken might do it if we don't like to eat red meat. So anyway, it's a nice big cycle. Nature is pretty ingenious. We can also take excess glucose, use a process called glycogenesis to make glycogen, and store that in our liver and our muscles, so that if we get low on blood sugar, we can break that apart by glycogenolysis to give us a sugar supply. So it's a little reserve. And if we have way too much glucose, we'll run it through a process of lipogenesis and make fat molecules from it and store those in adipose tissue. There's an animation here about the hydrolysis of sucrose. That might be worth watching. Here's another term that I told you about early on, gluconeogenesis, which means genesis, creation. Neo, new, glucose. So it is creating new glucose. It's taking parts of amino acids and the, oh goodness, cerebral flatulence here, brain's locked up, the glycerin from triglycerides and making new glucose from it. So that's production of new glucose. That can happen if your blood sugar level gets way too low. Cells can use carbohydrates as starting material for synthesizing vital biochemicals like 5-carbon sugars, ribose and deoxyribose. So remember now, the sugars we just looked at, the glucose, the fructose, they had 6 carbons in them. Ribose and deoxyribose only have 5 carbons in them, and hopefully you recognize those as ribose as being used in ribonucleic acid, better known as RNA. Deoxyribose is the 5-carbon sugar found in deoxyribonucleic acid, or DNA. And they mention lactose, or milk sugar, which the body can make when breasts are actively secreting milk. Okay, carbohydrate requirements. I don't normally spend a great deal of time on this. It really depends on the individual, but you need at least 125 to 175 grams of carbohydrate a day, although most of us probably get more than that. It says the average diet has 200 to 300 grams of carbohydrates. It depends again on what you're doing, how active you are. That determines how much you need. And as far as the diet goes, if you're eating French fries and rice and potato chips, you're getting probably more carbs than you need. Okay, so that is it for the section on carbohydrates.